Hey Susmita, shall we discuss continuity with madam today?
Yeah, okay, I'll find out from ma'am if she is free.
Yeah, let's see.
Hello. Good morning, ma'am. Ma'am, Kuntal and myself, we want to discuss some topics related to continuity. Are you free anytime today, ma'am?
Yes, I have a meeting at 11 o'clock. Now I am free. So make it soon. We will discuss.
Okay, ma'am. We'll be there in 2 minutes, ma'am.
Bye. Bye.
Bye, ma'am.
What did you say?
Ma'am is having a meeting at 11 o'clock, so we need to go now.
Okay, let's go.
May I come in, ma'am?
Yes, come in. How are you?
Yeah, we are fine, ma'am.
Sit down. Sit down, Sushita.
How are you, ma'am?
Oh, I am fine. So yesterday evening I had thoroughly enjoyed our discussion.
We also enjoyed. We enjoyed both the food.
Oh.
Means food for stomach and food for thought also.
Oh, that's nice.
You mean the cake and the power of continuity?
Yes. Actually, ma'am, we thought that we will discuss what continuity mathematically means with you. Actually, we have some idea, but it will be better if we discuss with you. That's why we came.
Oh, that's nice. Yes, literally continuity means uninterrupted connection, uninterrupted succession and consistent, unbroken existence of an entity over a change of a parameter. Say time. So you see a parameter changes and there is another entity which also changes as the parameter changes.
Is it okay for you?
Ma'am, can you elaborate?
Yeah, consider for example a particle traveling along a straight line.
Okay.
From time t equal to 0 to time t is equal to t.
Okay.
And let the distance travelled by the particle be denoted by s. Then you have an independent variable t, we call, which is a parameter in this case, and you have a dependent variable s, which varies as the independent variable varies.
Okay.
We say in mathematical parlance, s is a function of t. So let us consider the plot of y is equal to 2x plus 3 for x in the interval minus 2 to 2. Alright. So let us try to plot this graph. So the graph intersects the x-axis at minus 3 by 2, 0 and the y-axis at 0, 3.
Yes.
And x runs between minus 2 and 2. So the graph has been drawn for x values between minus 2 and 2. So look at the graph. We see that this graph has no jump or gap or break. So graphs of the plots which have no jumps or gaps are called continuous graphs.
Okay.
And therefore the graph of this plot is continuous. On the other hand, if I consider, say, the graph of the plot of y is equal to x for x less than or equal to 0 and it is x plus 1 for x greater than 0. Let us draw the graph of this plot. So it will be y equal to x for x less than 0 and y is x plus 1 for x greater than 0. And so you see that at x is equal to 0, there is a jump.
Yes.
So the graphs of plots which have jumps are called discontinuous graphs, or the graph of this plot is not continuous. Is it okay?
Yes, ma'am. It's okay.
Is it okay?
Yeah.
Fine. So to make things more mathematical, we must introduce some mathematical objects, rather mathematical concepts.
Yeah. So in these two relations, we see that they are functions.
Yes.
There is a dependent variable y and an independent variable x. The independent variable x varies over a set called the domain of the function.
Yes.
And the dependent variable y varies over a set called the codomain of the function.
Yes. So this brings me to the definition of what a function is.
Yeah.
So a function f from a set A to a set B is a rule which assigns to each element A in a unique element in B, which we denote by f of A. So this A is called the domain of the function f, and B is called the codomain of the function f. So if f is a function from A to B, taking an element A in A to an element f of A in B, we say that f of A is the image of A in its domain, namely A.
Okay.
So, can you now make some observation about the image of each element in the domain?
I can only say that for each element A in the domain, I have a unique image in the codomain.
Yes. Let us see in the example that we have considered, namely in y is equal to 2x plus 3, where x belongs to minus 2 to 2. So, in this case, there is a function f from the closed interval minus 2 to the whole of the real numbers. So that this closed interval minus 2 is the domain of the function, and the set of real numbers is its codomain, such that every element x in minus 2 to 2 is mapped onto an element f of x, which is 2x plus 3, and this belongs to the codomain R.
Okay.
So here we see that according to the definition of the function, we have that every element has a unique image. But is it possible that many elements in the domain go to the same element in the codomain?
Yes. Is it possible, ma'am?
Is it possible? Let's consider this example. Suppose we have a function f which is 1 for x less than 0 and it is equal to 2 for x greater than or equal to 0. And let us draw the graph of this plot. So it is 1 for x less than 0 and it is 2 for x greater than or equal to 0. So what is the domain of this function?
The domain is full real number.
Yes. What about codomain of this function?
The codomain is again R.
Yes, the codomain is again R. So we have a function from R to R. So the question now is, what is the image of negative real numbers?
The negative real number goes to singleton 1.
Yes. What about the image of the non-negative real numbers?
All the non-negative numbers go to 2.
Exactly. So this answers your question. So every negative real number has its image to be 1. Every non-negative real number has its image to be 2. Right? That answers your question.
Yes, yes.
So, you see that many elements in the domain may have the same image in the codomain. Is it all right?
Yeah, but I have one question.
Yes, sir.
Is it necessary that the domain and codomain, these should be subset of real number?
Not necessarily be. Suppose I give you two sets, say A. The set A consists of elephant, tiger and bear.
Okay.
And the set B consists of, say, table and chair. Right? So now I want you to give a function from A to B, taking A as its domain and B as codomain of the function f. Can you give me an example of a function?
One function that immediately comes to my mind is
Yes.
I will define f from A to B
Yes.
as all the elements in the domain going to table. So f of elephant is table, f of tiger is table,
Okay.
and f of bear is table.
Okay. Fine.
Yeah.
Oh, that means we only need a rule to connect elements in A to elements in B.
Fine.
Then I can give another example, ma'am.
Yes.
I can just remove this table with chair.
Okay. Fine.
Yeah.
All right.
Then
So,
it will be another example.
the examples of functions that you have given me are constant functions. So that brings me to the definition of a constant function.
Okay.
So what is a constant function? A function f from a domain A to a codomain B is a constant function if f of x is equal to f of y for every xy in the domain A.
Okay.
So, can you now think of other functions which are not constant functions from domain A to codomain B?
Yes, ma'am, we can think of.
Yes.
Means I can only change say if of elephant is here, tiger is here, I can change that BR to be table. Then I have a non-constant function because f of tiger and f of BR are not same.
Yeah. So
it is a non-constant function.
that is fine, correct.
So from this we see that every element in the domain has two choices, either table or chair.
Yes.
So the number of functions will be 2 into 2 into 2. So we have 8 functions from a 3 element set to a 2 element set.
That's
so
fine.
I can generalize for m and n also. Means if I have m set in A, m elements in the set A and n element in the set B, then for each element in A, so A has m element and B has n element.
Okay.
Then for each element in A, I have n choices.
Yes.
So there will be n into this up to m times. So total n power m function will be there.
Yeah, that's fine. This is how mathematics or any science grows.
Yeah.
You make observations and it leads us to more inferences. But you have missed out an important observation. Can you just think of what observation is that? No? An element in the codomain may not have a pre-image in the domain. That can happen.
What is pre-image?
That you have missed out. An element in the codomain B may not have a pre-image in the domain A.
What is pre-image?
Okay, let us consider our example which we had taken in the beginning. Namely, f is a function from -2 to 2 to the whole of real numbers defined by f of x is equal to 2x plus 3. Right? For every x in -2 to 2, the image is f of x, which is 2x plus 3. Now, if I consider any a in -2 to 2, then by definition, it goes to 2a plus 3, which is in the codomain R. So, I now consider an element 0 in the codomain R.
Okay.
Right? Then I can find an element -3 by 2 in the domain which is -2 to 2 such that f of -3 by 2 will be 2 into -3 by 2 plus 3, that is 0, which belongs to the codomain R. So this tells me that this element 0 has a pre-image -3 by 2 in the domain of this function f.
Okay, that means whenever f of A is B, we say A is the pre-image of B.
Yes. So let us now find out all the elements in the codomain which have pre-image. Suppose say B is an element in the codomain, then you must find elements A in -2 to 2 such that f of A is equal to B. That is 2A plus 3 must be B, or A is B minus 3 by 2. But you know that A should belong to -2 to 2. So this implies that B must belong to -1 to 7, which means those numbers B in the interval -1 to 7, which is a subset of the codomain R, will only have pre-images in the domain -2 to 2.
Yes.
So if you consider an element, say y, which is in the codomain R, and y belongs to minus infinity to minus 1, union 7 to infinity, then y does not have a pre-image.
Okay.
Is that clear?
Yes, ma'am. It's
Okay, now let us consider this example which we have taken earlier. We had a function f which takes values 1 for x negative and it is equal to 2 for x greater than or equal to 0. What can you say in this case?
In this case, every negative real number is a pre-image of 1 and every non-negative real number is a pre-image of 2.
Yes. So, you have a set consisting of elements 1, 2 as the image set and it is a subset of the codomain R because this was a function from R to R. So, the set of all f of x such that x belongs to A is called the range of the function f. So, you observe in this case that the range is the set 1, 2 and is a subset of the codomain. If for a function f from A to B, the range of f is equal to the codomain of f, then you say that the function f is an onto function or a surjective function. Alright. Okay. Our goal was to discuss about the properties of continuous functions. So, let us focus our attention on real valued functions of a real variable. So, does this statement make any sense for you?
Yes, it means we are considering functions whose domain and codomain are subsets of R.
Yes, exactly.
Earlier you were telling that continuous means there should be no jump or break or no gap.
Yes, we should now make these statements more mathematical.
Yeah.
So, let us consider a real valued function from the closed interval AB to the set of real numbers defined for elements in AB which are the set of all real numbers such that A less than or equal to X less than or equal to B with A less than B.
Okay.
Then let us consider a number x0 and fix that number and x0 is in the domain AB. So now there are numbers which are close to x0 in this interval AB. What I mean is there are numbers x which are at a distance from x0 such that the distance is very small. Or in other words, there are numbers x in the interval AB such that the distance of x from x0 in R is very small.
So what do you mean by distance, madam?
Yeah, let us draw the number line and plot 2 points which are real numbers C and D. Then by a distance between C and D, I mean C minus D or D minus C, that is the absolute value of C minus D. Is it clear?
Yeah.
Okay, ma'am.
So, when we draw the plot of the graph of this function f from AB to R, for points x which are close to x0, namely we have fixed that point x0 in AB. So, for points x close to x0 belonging to the domain AB, we want the images of x under f, namely f of x to be close to f of x0 belonging to the codomain. This is what we want in order that the graph of the plot of this function f has no jump, gap or break.
Okay.
So let's just understand it from the example that we have taken. Namely, we had a function f from minus 2 to 2 to the whole of r, defined by f of x is equal to 2x plus 3. So what should we do? We must fix a number x naught. So I take a x naught where in the domain minus 2 to 2 and I fix this x naught. So now I look for all numbers x which are close to x naught such that the distance between x and x naught is less than, say, 0.1.
Okay.
Then I consider the distance between their images. So it will be f of x minus f of x naught in absolute value. That is, it will be 2x plus 3 minus 2x naught plus 3. So that will be 2 into x minus x naught in absolute value. But my x is close to x naught and the distance between them is less than 0.1. So this means that this is less than 0.2. So this tells us that when x and x naught are close to each other in the domain minus 2 to 2, the corresponding images f of x and f of x naught are close to each other in the codomain. It is for this reason that the plot of the graph has no jump or gap or break. Is it clear now?
Yes.
Okay.
Right? Let us now see in the case of the example f, which is 1 for x less than 0 and 2 for x greater than or equal to 0. What can you say in this case?
I can only say that it has a jump at the point x equals 0.
Yes, it
from
has.
1 to 2.
Yes, exactly. So this tells us that for a function f to be continuous at a point x naught, which belongs to its domain, say A, right? We must have points x close to x naught be mapped onto points f of x and f of x naught which are close to each other in the codomain B.
This distance is a relative term. So how can we make this distance concept to be mathematically precise?
Okay, let us suppose that we want f of x to be close to f of x naught by a distance less than a given epsilon positive. Then this, so I want f of x to be close to f of x naught. These are in the codomain B. This I can achieve by coming close to x naught, where x naught belongs to the domain A. So I can come closer and closer to x naught by a distance which depends on this given epsilon positive.
Okay.
That is, given an epsilon positive, I can find a delta positive such that if x and x naught are such that the distance between x and x naught is less than delta, then the image of x, namely f of x, will be at a distance less than epsilon from f of x naught.
Okay.
So that is, distance of f of x naught from f of x is less than epsilon.
Okay.
Is that right? So, can you now say what happens in our example?
Can you illustrate this with some examples, ma'am?
Yes. Let us take the constant function that we had defined. Suppose I have a function f from a to b defined by f of x is equal to a constant c for every x in the domain A. Alright. So, I must check whether this constant function is a continuous function at some x naught belonging to the domain A. So, I consider points x which are close to x naught. So, let us look at the images of x naught in A and points x which are close to x naught in A. So let me find the distance between their respective images f of x and f of x naught. Then f of x is C, f of x naught is also C, and so this is 0, which tells me that whatever be the delta that I choose, which is a positive number, such that whenever the distance between x and x naught can be made less than delta, this implies that the distance between f of x and f of x naught can be made less than epsilon.
Yes.
So this tells that this constant function f from A to B is continuous, right, at the point x naught. So we have f to be continuous at x naught. But x naught is an arbitrary point that we have chosen in the domain. The argument holds good for any x naught in A, and therefore this constant function is continuous at every point x naught in its domain. For a given epsilon greater than 0, we may choose any positive number as delta, and the requirement for continuity is satisfied. So Kuntal, can you now show this for an identity function?
Yes, sure, ma'am. I can try.
Try. Why don't you try?
So, identity function, it is from real number to real number, defined as identity of x is x. Means every number is going to itself. Now I have to justify whether this function is continuous or not. So as earlier, I will take some x naught in real number and I will justify whether this is continuous at x naught or not. Now I will choose some epsilon positive.
Yes.
I have to find one delta.
Correct.
Now id of x minus id of x naught, it will be mod x minus x naught. Now I need these to be less than epsilon.
Yes.
So, and I have to fix some delta.
Yes.
Now if I take this delta to be equal to epsilon,
Correct.
then id of x minus id of x naught will be less than epsilon.
Yes.
So for this epsilon I get one delta.
Correct.
So this says that from the epsilon delta definition that id is continuous
Correct.
at x naught.
Fine.
Now since x naught is an arbitrary point, so id will be from R to R is continuous on whole of R.
So at all points in its domain, it is a continuous function.
So the first example that we considered was f was defined from minus 2 to 2 to r as f of x is equal to 2x plus 3.
Fine.
In this case, suppose we fix an x naught in minus 2 to 2. I am fixing it. Now, if I consider images of f of x naught for x close to x naught, that is modulus of x minus x naught is less than delta. So modulus of x minus f x naught will be modulus of 2x plus 3 minus 2x naught plus 3. So this is 2 times mod x minus x naught. We need this to be less than epsilon. Yes. So if I need this to be less than epsilon, so I choose delta to be epsilon by 2.
Okay.
So then I will have modulus of f of x minus f of x naught is equal to 2 into mod x minus x naught, which is less than 2 into delta, which is equal to epsilon. So I will have mod f of x minus f of x naught to be less than epsilon. So this shows that the function defined f is continuous at x naught.
Yes.
Since x naught is arbitrary, this function is continuous in the entire domain minus 2 to 2.
Yes. Do you think using epsilon delta definition to show that a function is continuous at a point is a difficult task?
No, it's very simple.
It is very simple. Now that you know how to use epsilon delta definition to show that a given function is continuous, let us take the example where there was a discontinuity at some point. So let us consider this function f, which takes values 1 for x less than 0 and 2 for x greater than or equal to 0. You had made an observation that it has a jump at x is equal to 0. So let us see what happens when x is different from 0. So let us consider the case when x is greater than 0. Then in that case, I can find a delta positive such that x minus delta to x plus delta is a subset of 0 to infinity. Right?
Yeah.
Then if I take a y in x minus delta to x plus delta, then the distance between the image of y, namely f of y, and that of x, namely f of x, will be 2 minus 2. Which means at all points x greater than 0, you have continuity of this function.
Yeah.
Because by epsilon delta definition, the condition is fulfilled. And that is why you did not observe any jump or break in the graph of the plot of f of x for x greater than 0.
Yeah.
The same argument holds good for x less than 0.
Yeah.
There was no jump or break. But you did make an observation that at x is equal to 0, there is a break. So, can you now explain using delta epsilon definition, right, regarding the occurrence of a jump at this point in the graph of the plot?
Let me try.
Yeah, try.
So, now the point that I am considering is, so my x naught is 0.
Yes.
So, suppose I take a delta positive. Let me take x to be minus delta by 2. Then modulus of x minus 0.
So, why do you take x is equal to minus delta by 2? So, you want to take points which are close to 0.
Yeah.
So, you are taking now the negative real number, which is close to 0.
Yeah.
Fine.
So, modulus of x minus 0 will be modulus of minus delta by 2 minus 0, which is equal to delta by 2.
Fine.
Which is less than delta. So, now I have points x close to 0. So, now the images are f of x minus f of 0 will be, x is negative. So, f of x is 1.
Correct.
And f of 0 is 2.
Right.
So, I have this difference to be 1. Now, suppose my epsilon is such that 0 less than epsilon less than 1.
Namely,
then,
I give you an epsilon which is between 0 and 1.
Yeah. Okay. Then this difference will not be less than epsilon.
Right. Fine.
So, this shows by the epsilon delta definition that at x is equal to 0, this function is not continuous.
That is, you cannot find a delta such that whenever x and 0 are close to each other by that distance. That their images will be close to each other. That's what you are saying.
Yes.
And so, this tells or this explains why there is a jump at x is equal to 0 in the graph of the plot of this function.
Yeah.
Is that right?
Yes.
Okay, fine. So, all along we have taken examples which are very, very simple examples like a constant function, an identity function, a linear function and so on. So, can you use epsilon delta definition and show, say, a trigonometric function is a continuous function? Take any function that comes to your mind. Why don't you try?
I'll take the first function, the sin x.
Okay, take f of x is equal to sin x and see whether you can show using epsilon delta definition that it is a continuous function. Just try.
So, I have to prove continuity of sin x.
Fine.
Where f is from real number to real number.
Fine.
Now, To prove continuity, I will first fix some x naught in
Yes.
the domain and I will fix some epsilon positive. I have to find a delta.
Yes.
Now, what is f of x minus f of x naught? This will be mod of sin x minus sin x naught.
That's fine. Before that, I would like to ask you a question. So, can you show that sine theta is less than theta when theta is positive?
Yes, ma'am, I can show it by using geometry and arc length formula.
Okay, fine.
But why I need this now?
You will see when you continue with your computations.
Okay. So these I can write as using sin a minus b formula. This will be sin x minus x naught by 2 cos x plus x naught by 2.
Fine.
So now cos of theta is less equal 1 for every theta. So this I can write as 2 sin x minus x naught by 2.
Fine.
But even sine theta is less than or equal to 1, right? Modulus of sine theta is less than or equal to 1.
Yeah, but the thing is, whenever we are discussing this continuity with epsilon delta, we need something like x minus x naught.
Okay.
That's why
Whenever x is close to x naught by a distance less than delta, you want to show the corresponding images
that's why I am
are close
just
to each other.
removing the cosine term.
So
Okay, there
he
is
wants
an
to
x.
retain this.
Okay.
Yeah.
Okay.
Yes, fine.
But now,
What happened? So you
how
are
to
unable.
get rid of the sign?
Yes, what about you?
No idea.
Don't you think modulus of 2 sine x minus x naught by 2 is equal to modulus of 2 times sine of mod x minus x naught by 2?
Okay, yeah.
Oh, yeah.
Can you explain why?
Yeah, because sine x and sine minus x, they have the same value with only negative sign. So if I take modulus, I will get the same.
Yes.
Okay.
So,
Yes.
so that's it.
use that.
Oh, now I can see this also. Why you wanted me to have sin theta less than theta
Yes,
for theta
exactly.
positive.
Exactly.
So now I can write it as 2 x minus x naught by 2.
Yes.
So it will be mod of x minus x naught.
Correct.
Now I have to get f of x minus f of x naught. I need this to be less than epsilon for some
Given epsilon positive.
for some x minus x naught less than delta. So I can take delta equal to epsilon
Yeah.
as earlier case also.
Yes.
So in this case I take delta equal epsilon and it will work. So from the epsilon delta definition I can say that sin x is continuous at the point x naught.
Correct.
Since x naught is any arbitrary point on real number, so I can say that f R2R what is defined as sin x
Correct.
is continuous on whole real number.
Yeah, that's fine. So you can now discuss the continuity of other trigonometric functions
We can.
Even
using
e power x,
e power x,
log
log x. All those functions can be discussed
Yes.
using epsilon delta definition. So try to work out. But
Okay, ma'am.
before that, I have a question. So if a function f is continuous from a to b, and I want to show that f is continuous at x naught, then given an epsilon positive, there exists a delta 1 positive such that whenever mod x minus x naught is less than delta 1, it implies that mod f of x minus f of x naught is less than epsilon. So the question now is, given an epsilon positive, does there exist another delta which is positive such that modulus of x minus x naught less than delta implies modulus of f of x minus f of x naught is less than epsilon?
Yes, ma'am. It will be easily, because if I take any delta less than delta 1,
Okay.
Yeah.
means if I take any delta less than delta 1,
Fine.
and if I take x minus x naught to be less than delta, which will be easy less than delta 1,
Yes.
then f of x minus f of x naught, it will be less than epsilon. So any delta less than delta 1 will work.
Yes. Fine.
So we actually have infinitely many deltas.
Yes.
But we only need only one delta for the definition, sake of the definition.
Exactly. Yes, you are right. So, I have, it's already time. I have another meeting to attend to. So, we shall stop our discussions here. But I have a lot of examples to discuss, and I want you to do some more examples.
Yes, ma'am.
To have a better understanding of the properties of continuous functions. We will continue with this discussion tomorrow.
Okay, ma'am.
Yes. Okay. Yeah, that's nice. See you then.
Okay,
Bye.
ma'am. Bye.
Yes.